A base large language model is essentially a massive, high-powered statistical engine. It predicts the next word, spinning out raw text, without specific direction. To steer that raw power toward useful, safe behavior, we use post-training data. The effectiveness of this post-training phase relies completely on how we structure the information we feed. Transitioning a model from simply reciting facts to executing complex logic or optimizing its own answers requires us to change the specific topology of the training data. If the data pipeline lacks the correct structural blueprint, the computational power of the foundational model remains wild and undirected. To align an AI, we typically build towards 3 distinct behavioral goals, requiring 3 specific architectural pathways. The first pathway creates standard instruction following, where the model learns from direct static examples. The second establishes a chain-of-thought capability, forcing the model to show its logic using syntactical boundaries. The third pathway introduces dynamic optimization, utilizing reinforcement and environmental grading to improve responses over time. Because these objectives demand completely different computational behaviors, they rely on entirely different underlying data architectures. We begin with supervised fine-tuning, or SFT. This is the bedrock of teaching a model to follow instructions, and it relies on the simplest data topology. The core structure of SFT data is a strict, immutable pair, consisting of a user input and a target output. This slide shows a sample fine-tuning data pair. The input asks how many apples Alice has after starting with 3 and buying 2 more, and the target output simply reads 5. This topology trains the model to establish a direct mathematical mapping from the specific text of the prompt straight to the final answer. However, this format presents a serious limitation. It bypasses any intermediate logic required to solve the problem step by step. While SFT ensures the model complies with the requested format, its static nature means we are teaching the model what the final conclusion should look like, rather than the process of arriving at it. To move past simple mapping, engineers face a specific challenge: how to compel the model to generate and expose its intermediate logic before finalizing an answer. The solution is a structural change. We modify the target output by adding explicit syntactical boundaries. This updated data schema shows how the intermediate logic is isolated. Inside the target output, we inject a think block containing the mathematical steps, positioned explicitly before the final answer tag. By requiring these XML-style tags, we force the model to output reasoning tokens one by one, functionally creating a computational scratchpad. Structurally, this remains a data pair. What we observe as reasoning in large language models is not a sudden cognitive leap. It is a specific text generation behavior, programmatically enforced by strict syntactical formatting during training. Both standard SFT and explicit reasoning formats rely on perfect, human-curated target outputs. For highly complex tasks, handcrafting these targets becomes impossible to scale. To scale capabilities further, we introduce reinforcement learning, or RL data. This approach discards predefined target outputs completely. Instead of referencing static text pairs, the system shifts to live generation. We feed the model a list of inputs, and it generates answers dynamically. We call this live generation a rollout. Since there is no predefined answer key, rollouts must be evaluated against an external grader to determine quality. This completes the new data topology by accunding a numerical value, forming a 3-part tuple consisting of input, output, and reward. Transitioning to a dynamic reward tuple allows the model to stop mimicking human text and mathematically optimize its problem-solving performance. In reinforcement learning from human feedback pipelines, this tuple can expand to include multiple model outputs and a label indicating which response is preferred. But regardless of whether you train on pairs or tuple, the entire dataset must be rigorously partitioned. We segment the data into a training set to update neural weights, a validation set to tune hyperparameters, and an isolated test set to evaluate final performance. Even the most perfectly formatted reasoning tuples lose their value if the dataset is not aggressively partitioned to verify that the model is actually generalizing its logic rather than just memorizing the training data. Ultimately, creating advanced behavior in a language model is an exercise in data formatting. We can see this evolution clearly when we look at the 3 architectural schemas side by side. The static pair yields basic instruction following. The syntactically bound pair produces enforced logic, and the reward tuple drives autonomous optimization. The final capability of any post-trained model is a direct reflection of these specific structural topologies. The entire post-training process lives or dies on the structural integrity of this data. Modern AI alignment is essentially the precise engineering of data architecture. To change the way a neural network processes information, you must first change how its universe of data is formatted.